Hello everyone, my name is Sujin Park and today I'm going to present our paper, Contextual Concurrency Control. With the introduction of multi-core machines, the parallelism and concurrency are the key for designing today's applications. And they rely on synchronization mechanisms that can be found in almost any software we can think of, as they are the basic building blocks. Having proper lock design are critical for application performance. This is a typical application performance on a multi-core machine, and as you can see in the graph, the throughput vary with the number of thread counts. Although application developers expect to have linear scalability with increasing core counts, this is far from ideal. Therefore, it is necessary to carefully choose which lock algorithm to use. However, even if one lock algorithm works well in a particular scenario, it can't be the answer in all cases. Since the hardware is always changing and there is a variety of applications and requirements, one system-wide lock cannot rule all of them. For example, Apple's M1 chip has 4 high-performance cores and 4 slower cores in one processor. And for better performance, developers may want to give faster cores more opportunities to grab locks. Also, although one lock works well in one application, it may not be a good choice for other applications or when a workload is changed. What is worse, as current lock design is statically compiled in the kernel, changing a policy will modify all the locks together in the kernel. Despite the fact that synchronization is such important to application performance, they are usually invisible and out of reach of application developers. Instead, kernel developers make older decisions regarding kernel lock design. In many domains, specialization seems to be the answer for this sort of problems, as it can bridge the semantic gaps between applications and the kernel. While specialization have been studied for storage, network, and accelerators, concurrency control hasn't been exposed to applications. So here our question comes. Can we tune lock policy on the fly? In our work, we propose contextual concurrency control, a new paradigm to tune synchronization mechanism from the user space. Looking at the following problems, the need for user-defined locks on the fly is pretty clear. First of all, current lock implementations are application agnostic. That is, lock algorithm doesn't know the context of application running on it. Also, since only few locks contend for a given application, we don't need to change all locks together in the kernel. Finally, we may need a variant of a lock based on the workload. To showcase our idea, we designed and implemented Concord framework. With our framework, now an application developers can tune locks in the kernel on the fly without recompiling the existing kernel code. Instead of changing all locks together, now user can modify a set of locks at various granularities. And lastly, our framework exposes a set of APIs to modify lock algorithms. Here's the Concord overview showing how to apply a user-defined policy. First of all, user creates a lock policy. For instance, if user wants to reorder waiters in the waiting queue to have better performance on a NUMA machine, they need to move a waiter forward to group waiters together in the same socket. To implement the policy using our API, user only need to write simple code to compare socket ID between two given nodes and return true or false. Then the verifier checks and decides whether the policy written by user is safe to load or not. With limited memory read and write access, we can ensure that locks won't be changed arbitrarily. In addition, It is also guaranteed that the policy calls only whitelisted functions, and users' policy will not hang inside. If you apply these restrictions on the example policy, we first check read access for node pre and cur, and check whether the policy calls any functions outside from the whitelist, and then also make sure that there are no loops inside the policy. Once the policy passed the verifier, user need to select where to apply the policy. Concord can tune locks in fine-grained manner at different level of granularity. For example, user can change all the spin locks in the kernel, or only spin locks used in file system, or even a single spin lock instance used for an inode. And finally, Concord hooked the existing locking function to run with a given policy for the specified locks. Concord provides several APIs for users to easily change locking functions' behavior. For example, it exposes compare node function, which will be used as a comparison function when reordering waiters in the queue. Or user can simply turn on and off reordering behaviors using skip shuffle function. Using these APIs, user can implement various locking policies themselves and change underlying lock on the fly. In addition, thanks to the ability to patch only selected locks, we can now profile locks in fine-grained manner by selecting only interesting points. To be specific, user can inject their own code before acquiring a lock when a lock is contended, after acquiring a lock, or after releasing a lock. Although users might implement some bad policy that may break fairness guarantees, or heavy profiling might increase critical section, our runtime checks ensure the mutual exclusion and it's safe from crashing. Here's one use case with a simple example. Let's say there are two tasks, T1 and T2, spending a large fraction of time to acquire a same lock. If T2 holds a lock 3 times longer than T1, it will receive 3 times much CPU than T1. Although the lock ensures fair acquisition order, this is an example where lock usage pattern might break the goal of the scheduler, which want to give each thread an equal share of CPU. To solve this issue, SCL lock keep track of the lock holding time and penalize T2 so that T1 can have more opportunity to grab a lock. Although this solution addressed the problem, it enforced this fairness even for applications that might not benefit from it. With our idea, application developers can use the exposed APIs and enforce this special fairness only when needed. This is one example of how our framework can be used, and you can find more use cases in our paper. Now, let's see how much overhead will be introduced to use dynamically changing lock design compared to the pre-compiled lock. Here, we implement the Bravo lock on Concord framework and compare it with the pre-compiled version without Concord. As you can see, Concord has almost negligible overhead in micro benchmarks that severely stress the lock. And remember, now we can change lock on the fly. In conclusion, kernel locks are critical for application performance and scalability, but they are out of reach of application developers. We proposed C3, Contextual Concurrency Control, to let user-space applications to fine-tune concurrency control on the fly. To demonstrate the C3 potential to improve application performance and scalability, we implemented Concord framework. The framework exposed a set of APIs so that users can write their own code to modify the kernel locks. The modification can be applied to only specific target locks instead of changing all locks in the kernel. And we showed that our framework can change locks on the fly with minimal overhead. Thank you for your attention.